In the last lecture, we took a look at something called the equilibrium constant for chemical reaction. What we discovered was that for any equilibrium system at a given temperature, there exists this equilibrium constant, and we also learned how to write the expression for that constant. The most important thing we learned was that although the individual concentrations of the reactants and products will be different for different equilibrium states, in fact, we saw 6 different equilibrium states for a hypothetical reaction, and even if these individual concentrations varied all over the map, when the numerical values for these equilibrium concentrations were plugged into the equilibrium constant expression, they always produced the same number, namely the numerical value for the equilibrium constant for that reaction at that particular temperature. For example, for the reaction you see on the screen, the equilibrium constant expression was equal to the concentration of C squared times the concentration of D to the 4th power divided by the product of the concentration of A cubed times the concentration of B. We learned how to write these kinds of expressions, and when the system is at equilibrium, the numerical value of that expression will just equal the numerical value for the equilibrium constant for that reaction at that temperature. Well, that's very nice, but I think one can probably ask the question, so what? What am I supposed to do with these equilibrium constants? What are they supposed to tell me really about a chemical reaction, and why are they so important? Well, let's try to answer those questions. To keep this discussion as simple as possible, we'll use a very simple reaction. A plus B produces C plus D. We know how to write down the equilibrium expression for K. It would equal the concentration of C times the concentration of D divided by the product of the concentration of A times B. And at a given temperature, this expression would always equal the same number, namely the equilibrium constant. So why don't we ask this question first? What is the possible numerical range that equilibrium constants can assume? How large can they be? How small can they be? Well, they have as large a range as would ever be possible, basically from 0 to infinity. Now, how do we arrive at that conclusion? Well, first we know that equilibrium constants couldn't possibly be negative numbers. In order for an equilibrium constant to have a negative value, at least one of the substances in the equilibrium would have to have a negative concentration. Well, you can't possibly have a negative concentration. A concentration can't ever be smaller than 0. So we know that equilibrium constants couldn't be negative numbers. Well, how small could they get? Well, let's look at this mathematically. If one or both of the concentrations of the products were to get real close to 0, in fact, let's pretend one of them was, for all practical purposes, as close to 0 as you could get. Well, if the concentration of C were essentially 0, then the numerator in the expression for K would equal 0. It wouldn't matter what the concentration of D was, because when you multiply any number by 0, you still get 0. And if the numerical value of the numerator is 0, then the numerical value for the entire expression would be 0. So the numerical value for an equilibrium constant could be very, very small, essentially as close to 0 as you could imagine. The smaller the value for the concentration of one or more of the substances in the numerator, the smaller the value for K. Since these concentrations can get very close to 0, the numerical value for K can get real close to 0. Well, how large can the value of K be? All we have to do is simply reverse the logic. Suppose the concentration of one or both of the reactants gets very close to 0. That would mean that the denominator of this expression would get real close to 0. But what does that mean mathematically? That's easy to say. As the denominator of a quotient approaches 0, the value of the quotient will approach infinity. That sounds very good. That's the way teachers often like to talk. But let's see what that really means. Let's suppose I had the number 12, and I made the denominator 6. Then the value of the entire quotient would be 2. Well, suppose I made the denominator smaller, let's say 4. Then the value for the quotient is 3. you notice that the value for the entire fraction is becoming larger. As the denominator became smaller, the value of the fraction became larger. If I make the denominator smaller, 3, then the fraction becomes even larger, 4. If I continue this process and divide by 2, it becomes 6. If I make it 1, now it's up to 12. As the denominator gets smaller, the value of the entire quotient gets larger. If I make the denominator pretty small, 1/100th, 0.01, then the entire fraction has reached the value of 1200. Now perhaps you can extrapolate this thought process. As the denominator gets smaller and smaller and smaller and smaller, the value of the entire number gets bigger and bigger and bigger and bigger. Now perhaps our original statement is clear. I know that for many of you it may have been clear immediately. As the denominator approaches 0, because one or more of the concentrations is close to 0, the numerical value of the equilibrium constant will get larger and larger, and in fact will basically approach infinity as the denominator approaches 0. I often like to make the joke that equilibrium constants vary from the smallest positive number in the entire universe, the number that comes right after 0, to the largest number in the entire universe, the number that you run into just before you get to infinity on the number line. Well, I mean, that's a nice theoretical answer. Equilibrium constants can have a numerical range from essentially 0 to infinity. In practice, you're going to find that the actual numerical values for real equilibrium constants range from some of the smallest numbers you will probably ever encounter to some of the largest. It is actually not that unusual to see equilibrium constants with numerical values as large as 10 to the 100th power or even larger. That number boggles the mind. I mean, the largest number in the world is, something like Avogadro's number, 6.02 times 10 to the 23rd. And here's a number 10 to the 100th power. Equilibrium constants can be enormously large or incredibly small. Well, what does it mean if an equilibrium constant is large or small? I mean, for example, suppose the equilibrium constant for this reaction were a relatively large number. Let's just make up a value. 2.3 times 10 to the 15th. Okay, that's a nice number. But what are we supposed to make of that? I mean, what does it tell us about this reaction? And vice versa. If this were a very small number, what would that tell us? That becomes, believe it or not, a fairly sophisticated question to answer. If you ask a chemist or a chemistry teacher, what does it mean if an equilibrium constant is, quote, large? Now, the word large is pretty ambiguous. So large is typically interpreted to mean any number greater than 1. Obviously, if it's 1, I mean, it really isn't all that large. If it's 100, it's moderately large. 1,000 is kind of getting there. And if it's 10 to the 100th power, it's extremely large. But 1 is usually taken to be the dividing point. If you ask a chemist what a large value for K means, she is probably going to say one of two things. The products are favored, or equilibrium lies to the right. Now, does that make a whole lot of sense? Well, not in those words. It's kind of hard to know what that really is supposed to mean. The products are favored. What that kind of conjures up is images of, somehow or other the reaction likes the products. It likes to form the products if K is larger than 1. And what is meant by the phrase, equilibrium lies to the right? Well, in a chemical reaction, the reactants are written on the left and the products are written on the right. So when we say equilibrium lies to the right, what this means is that you, quote, tend to form the products. The products are, quote, favored. Equilibrium lies in favor of the products. This is still kind of ambiguous, but we're going to elaborate on this a bit later. Well, if you understand this or don't understand it, then the corollary statement that if K is small or less than 1, the reactants are favored, or equilibrium lies to the left, is equally understandable or not understandable. Based on these kinds of statements, it is immensely tempting to come to the following kind of conclusion. And this is not a silly or irrational conclusion. This is a very sensible conclusion. If K were equal the concentration of C times the concentration of D divided by the concentration of A and the concentration of B, and if the numerical value for K is a large number, like 2.3 times 10 to the 15th, you would be very tempted to say something like, oh, I know what that means. It means you have lots of products at equilibrium and very few reactants. And I would say that makes sense. In fact, if you want to reach that conclusion and remember it, fine. It's a reasonable conclusion, and it will serve you well almost all of the time. But technically, it isn't true, and I'd like to show you why. Mathematically, all that a large value for K tells you is that the numerator of this expression is large, and or the denominator of this expression is small, or some combination of the two. This would seem to imply that at equilibrium you would have a lot of products and or very few reactants. That a large K means you have lots of products and vice versa. A small K means you have lots of reactants. And as I said, if you want to come to that conclusion, I'm not going to tell you to forget it. However, as I said, it isn't always true. And I'd like to show you an example that illustrates this. This is somewhat subtle. If you don't follow all of this, don't worry about it. I mean, it isn't that critical. But I think we really should point this out. Let's take a simpler numerical value for K, just 10 to the 5th. This way the mathematics will be easier to follow. And this has to equal the concentration of C times the concentration of D divided by the product of the concentrations of A and B. I'm going to make up some equilibrium concentrations that will satisfy K. For example, let's assume that at equilibrium, the equilibrium concentration of C was 1/100th molar, 10 to the minus second molar. And the equilibrium concentration of D was also 10 to the minus second molar. While the equilibrium concentration of A was 10 molar, lots of A, 10 molar, while the equilibrium concentration of B was very, very small, only 10 to the minus 10th molar. Well, 10 to the minus second times 10 to the minus second is 10 to the minus 4th. 10 to the first times 10 to the minus 10th is 10 to the minus 9th. And 10 to the minus 4th divided by 10 to the minus 9th is 10 to the 5th. So these particular concentrations would satisfy K. This system would be at equilibrium. K for this reaction was a large number, 10 to the 5th. But do I actually have more products than reactants? Well, you may be tempted to say, well, yeah, you must have. I mean, the numerator is bigger than the denominator. But actually, you don't. The concentration of C is 1/100th molar. That means that there is 1/100th of a mole of C in a 1 liter container. The concentration of D is the same thing, 1/100th molar. The concentration of A is 10 molar. There are 10 moles of A in that container. Well, the concentration of B is so small, I probably just should ignore it, but we'll include it. It's 10 to the minus 10th molar. Now let me ask a different question. How many total moles of reactants are there in that container, and how many total moles of C and D are there? How many total moles of C and D are there, the products? Well, there's 100th of a mole of C, I'm assuming a 1 liter container, and there's 100th of a mole of D. So altogether, inside that container, there are only 2/100ths of a mole of products. That's all. That's not a lot of products. How many total moles of reactants are there, A and B? Well, there's 10 moles of A, lots of A. There's almost no B, 10 to the minus 10th of a mole, hardly worth adding in, but we'll add it in anyway, 0.00001, for a grand total of 10.0001 moles of reactants. So what's the point? Here's the point. The number of moles of reactants in this particular example is roughly 10 moles. The total number of moles of products is only 2/100ths of a mole. This system at equilibrium actually contains many more reactants than products, about 500 times as much reactants as products. Yet the value of K is being satisfied. Just because K is a large number does not mean that it must necessarily mathematically follow that you have to have more products than reactants at equilibrium. as this counterexample illustrated. This reaction has a large value for K, which says that the products are actually, quote, favored in this reaction. Yet we've just seen that it is possible, depending on the specific concentrations of the reactants and products, to actually have more reactants than products at equilibrium. So how might we possibly look at this? Well, I think it's reasonable to say the following. A large value for K says that you will tend to have more products than reactants at equilibrium. And a small value for K says that you will tend to have more reactants than products at equilibrium. Let me elaborate on that. The essential point is that while technically you don't have to have more products than reactants when K is large, this does tend to happen. I mean, essentially, if you give the system a fair shake and don't rig the concentrations, like making one thing 10 molar and another 10 to the minus 10th molar, if you don't use ridiculous values and just let everything be some normal numbers, I mean like starting out with 1 molar or half molar or something reasonable, if K is large, you will most likely have more products than reactants when you get to equilibrium. And if K is small, you will most likely have more reactants than products at equilibrium. Once again, there can be some tricky mathematical situations where this might not be true because the equilibrium constant for reaction requires that you raise the concentrations of all the reactants and products to powers equal to their coefficients in the balanced chemical equation. So some concentrations end up being more important than others. But I think the point has been made clearly enough. Okay, so if K is large, you tend to have more products at equilibrium, and if K is small, you tend to have more reactants, just the opposite. Well, that's fine and good and Jim dandy, but that brings us to the next question. Why is K so important? I mean, we've made such a big deal out of this. Why is K so doggone important? That's a question that's easily answered. In most of the remaining lectures, we're going to be working equilibrium problems. Now, when you are trying to solve any problem, you need some place to start. For example, we've worked a lot of stoichiometry problems. And when we worked stoichiometry problems, we found that the key to working these kinds of problems was the balanced chemical equation. If this is the equation I'm working with, that's where I started, because that allowed me to make statements like 2 moles of A will form 3 moles of C. For stoichiometry problems, the balanced chemical equation was our starting point. So what's your starting point for equilibrium problems? You've got to be able to write something down, and what you can write down is the expression and the numerical value for K, which will usually be given in most kinds of problems. For example, if I say to you, here's an equilibrium system involving the reaction A plus 2B in equilibrium with 3C plus 2D, and I want you to work some problem. I'm going to give you some information, and then I'll ask you something like, what's the concentration of C at equilibrium, or, whatever. You look for something that you can write down, and here's what it is. You are absolutely certain that no matter what the individual concentrations of A, B, C, and D are, the concentration of C cubed times the concentration of D squared divided by the concentration of A times the concentration of B squared is going to equal 4.9 times 10 to the minus 4th when the system is at equilibrium. You can have complete faith in that statement. That's the starting point for most equilibrium problems. And that's why the equilibrium constant is so important. That's the only thing that you can say with certainty. Let me put it this way. It's a difficult world we live in. I feel sorry for teenagers. I mean, it's tough being a young person. You're searching for some meaning in your life. You're looking for something, anything, that you can really believe in. And it's so difficult to find something, anything, in which you can put your complete faith. You turn on the news, you hear about corruption in government, corruption in industry. The world appears as if it may be heading for disaster, and you ask, what can I believe in? Perhaps you look towards religion for your beliefs, but maybe that doesn't work for you. Your parents may be helpful, but perhaps not. You look towards your teachers, but maybe they are of no help. You read the paper and learn that more and more nations are becoming armed with nuclear weapons, and you wonder, is that terrible day of Armageddon coming in my lifetime? So you search for something in which you can believe. Well, I want to tell you one thing. If the day ever comes when those nuclear weapons are launched, and if those nuclear weapons explode on every corner of the globe, I'm here to tell you that if the world were to turn into a primordial fireball, if the world may crumble, rising from that primordial fireball will come the symbol K. It is the only thing that you can have absolute faith in. It will always remain constant and unchanging. Well, assuming you don't change the temperature. One of my students was so impressed by this that he had a newspaper headline printed that said, "World crumbles, K remains constant." Oh, but that's assuming that you don't change the temperature, because we've learned that K is always constant for a given system at a given temperature. If we change the temperature, we will change the value for K. And in a couple of lectures from now, we'll learn how to predict what will happen to the value for K if we do change the temperature. I should make one comment here. Since the value for an equilibrium constant depends on temperature, chemists decided to specify the conditions at which most equilibrium constants will be measured. They call these conditions standard state conditions of temperature and pressure. Now you may be thinking, oh yeah, I remember that, STP, right? No, actually it isn't STP. STP was called standard conditions of temperature and pressure. These conditions were 0 degrees Celsius and 1 atmosphere pressure. Molar volumes of gases were referred back to these conditions. You know, our old 22.414 liters per mole. For equilibrium constants, they use what are called standard state conditions, sometimes called free state conditions. The only difference is that the temperature is 25 degrees Celsius instead of 0. These are basically room conditions. So anytime you see an equilibrium constant in these lectures or in your textbook, and you will see many of them before we are done, you can almost rest assured that that equilibrium constant has been measured at a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. Well, what we need to be able to do is interpret the meaning of an equilibrium constant. So let's take a look at 3 reactions that have 3 different values for their equilibrium constants. The first reaction is actually the ionization of acetic acid. We're going to come back to this in a later lecture and talk about it in great detail. The equilibrium constant for that reaction happens to be 1.8 times 10 to the minus fifth. The second reaction is one we've seen quite a bit in this course. Nitrogen gas and hydrogen gas reacting to form ammonia. And the equilibrium constant for that reaction is 4.1 times 10 to the 8th. The last reaction is carbon dioxide plus hydrogen react to produce carbon monoxide and water. And the equilibrium constant for that reaction happens to be 0.58. If necessary, stop the video and try to answer these questions. Of the 3 reactions given here, which would you consider to be the, quote, best example of equilibrium? By that I mean, which reaction would tend to have a significant amount of both products and reactants when it reaches equilibrium? Which reaction would you say, for all practical purposes, quote, goes to completion. And for which of these three reactions would you tend to say the reactants are favored? Okay, let's take a look at this. When we look at these three reactions and ask which is the best example of equilibrium, I guess, that's a somewhat ambiguous term. But what we mean by this is equilibrium systems don't go to completion. When you reach equilibrium, you still have reactants and you still have products. And the forward and reverse reactions are occurring, but at equal and opposite rates. So I guess the ideal equilibrium system, the king, the paradigm, you look that up, of all equilibrium systems would have to have an equilibrium constant equal to 1. Well, the last reaction has an equilibrium constant of 0.58. That makes it an excellent example of an equilibrium system. Given a fair shot, by that I mean if I start out with everything at something like 1 molar concentration or reasonably close to that for all the substances in the reaction, when I get to equilibrium, there's still going to be a significant amount of all 4 substances present: carbon dioxide, hydrogen, carbon monoxide, and water vapor. You'll have a substantial amount of both the reactants and the products. This is an excellent example of an equilibrium system. Now, which of these essentially goes to completion? Goes to completion means that it's basically a stoichiometry-like reaction. It just keeps reacting until one of the reactants is almost totally consumed. Now, since these are equilibrium systems, nothing can be totally consumed, but one of these has to get awfully doggone close, and that would be the second one. Since this system has a very large value for its equilibrium constant, and since the equilibrium expression for that system would equal the concentration of ammonia squared divided by the product of the concentration of nitrogen times the concentration of hydrogen cubed, and since at equilibrium this expression has to be equal to 4.1 times 10 to the 8th, which is a big number, that means that given a fair shot, when I get to equilibrium, I'm going to have lots of ammonia. I mean a plethora of ammonia, a veritable cornucopia of ammonia, and I'm going to have very little nitrogen and hydrogen left. This reaction, for all practical purposes, goes to completion. Well, after you've answered the first two correctly, that kind of tips off the answer to the last one, doesn't it? For which reaction are the reactants favored? Well, it's obviously got to be this one, doesn't it? Since K is very small, that means that the numerator of the equilibrium expression has to be small. There will be very little hydrogen ion and acetate ion present at equilibrium. And the denominator will be large. There will be a lot of reactants left at equilibrium. This reaction doesn't go very well at all. Okay. Now, in the last lecture, we saw that we can change equilibrium systems. We set up 6 different equilibrium states for the same equilibrium system that had completely different concentrations, but still satisfied K. It is possible to alter equilibrium states and then let them reestablish a new equilibrium. For example, I can increase or decrease the concentration of one of the reactants or products after the system has reached equilibrium by adding or removing something, and the system will then reestablish a new equilibrium after a time. Is it possible to make predictions as to what kind of adjustment will occur? That's what we're going to talk about in the next lecture.